Yeah, well, let's get started then. So I'll moderate this second session of the conference. So first, we're going to hear from Max Gronke, and just a reminder for those who might have just joined us. Each of these talks is 20 minutes long with a 10-minute Q&A session at the end. And since that's a pretty substantial Q&A session, let's try to keep most of our questions until the end of the talk, unless it's something that is really pressing for your understanding of the material. And as another reminder, we also have a discussion section for half an hour at the end of this conference session. And so if you have any questions that that we don't get to, then we can always talk about them in the half-hour open session later. So I'll hand it off to Max.
Thanks. Yeah, thanks, Chad. Do you see my main screen and hear me?
Yep.
All right, awesome. All right. Well, yeah, thanks the organizers for making this meeting. I also should say that I'm also a bit mad at you because I thought when you organized that, I thought it's going to be a 10 people meeting and so kind of casual conversations and discussion, and now suddenly there's 100 people. So I have to apologize in advance because this is not going to be as polished as my previous speakers, and it still shows a lot of work in progress. Yeah, sorry if I lose some on the way, because I also thought it's all going to be enthusiasts, but thanks a lot for the previous speakers who already gave some part of intro, because I didn't have any intro essentially. Okay, but let's start. So I mean, we heard a lot about this cloud crushing already, and as Pratik said, if this ratio of T cool mix over T cloud crush is larger than unity, then clouds will die, and if it's smaller than unity, then they will survive and can be fuel. This can be fuel for future star formation, trace for our outflows, and all the good things. So here in this talk, I want to mainly focus on implications of this and long-term evolution. Now, the first implication I want to show, and it's somewhat related to a question we had earlier, is about what happens if you put magnetic fields also in your wind and cloud, and what happens in the later evolution. And here I show a slide from one of these simulations where I start with a beta of unity in the hot medium and the cold medium, but you see because of this cooling supported survival and then further on cooling, you get this magnetic compression, so you end up with a beta much smaller than unity. And I'm excited about this because similar things or non-thermally supported cold gas has been seen in observations and now also larger scale simulations as shown this year. Now, the second implication I want to flash is the one of molecular outflows. So this has been something Ryan Farber, who is a grad student at the University of Michigan, has been exploring. And to do so, he put on in Lagrangian tracer particles inside these cloud crushing setups, as we also saw before. So on the left, we have a plot similar to what you saw before. So the cold gas mass evolution as a function of time, but this time varying the cold gas temperature. So that's a new parameter here. But you see for all these clouds, they would survive. But the nice thing here with these tracer particles on the right, he can basically check if dust or molecules would be killed in the hot medium, and with different line styles, he basically defined two different criteria of when he calls dust to be survive or not. And the takeaway message here is that molecules and dust can survive, but the surviving fraction really depends strongly on the details of this dust destruction. And this is because these dust particles, they would dip into the mixed medium before they maybe get entrained back into the cold medium. So, and also something, I mean, Pratik already talked a lot about this, but also something Ryan noticed in his simulations was that, some of them, they would be declared as dead, as in some of work in the literature, but, in fact, you find mass growth further on and rather quickly. So we would call them to survive. But and the last implication I want to talk about, and the reminder of this talk, is this continuous mass growth that happens, on a very long time scale, and that's maybe surprising because you would expect, that shear leads to mixing and therefore to cooling, as I mean, Drummond showed great talk during his great talk. But on the plot here to the left, I show you the mass growth rate of one of these simulations, shown in red. And, you see the mass growth rate flattens out, although the velocity difference shown in blue, becomes negligible further on as the cold mass is getting entrained. And what is happening here, you might infer maybe from this movie I show at the bottom, where this time I show the emissivity, so where the cooling is happening. And you can see within this cold medium, there are these waves and pulsations, and these pulsations lead to further mass growth and cooling, which therefore can be sustained on a timescale much longer than you would expect, from decaying turbulence otherwise. Now, in this work, we also quantified this mass growth earlier and estimated how much mass you could transport with this effect into the circumgalactic medium, and found, if you plug in numbers, it's actually not too negligible. But we also identified several potential issues with it. Oops, sorry about that. And the main one is, again, that of convergence. I mean, Drummond already said a lot about this. Okay, I'll show you the video again. I don't know how, yes. The main one is that of convergence. Drummond already, gave a great introduction of this. And, basically the reason is why is this total mass growth rate converged? And we checked that up to, being able to resolve CST cool in these cloud crushing setups. But our emissivity layer is in this one cell thick emission layer. And to get to the bottom of this, Brian Tan, who is a grad student at UCSB, he also simulated, in detail these shearing layers, similar to Drummond's work. And what he found is similar results to what we did in these larger scale simulations, namely, converged total mass growth rate, but this one cell thick emission layer. And he also found the scalings to be rather similar to these larger scale simulations. Oh, sorry, I should say, he also ran 1D results where, the behavior was much more than expected, right? That you only get a converged mass growth rate once you do resolve the field length. Okay, but he also found the scaling, the mass growth scaling, to be similar to what we found in these larger scale simulations. And there are a few kind of weird things about these scalings. First of all, why is it to first order given by the cold gas sound speed, although the hot medium can sustain a much larger mass growth rate? And then secondly, why is there this weird 1/4 scaling? And he also found, in fact, 1/2 scaling, which is consistent with Suching's work earlier of these turbulent mixing layers. And he found this transitional region here. Now, if you look in detail at these two regimes, you see, it's not just these scalings that become different, but the morphology of these mixing layers really changes. So in this weak cooling regime, and here I show you different slices, through one of these mixing layers, you see that there's much more 10⁵ Kelvin gas, so everything is kind of well mixed. Whereas on the right-hand side, in the strong cooling regime, you see that these interfaces between hot and cold medium are much more distinguished. For us, understanding this problem really came from an adjacent field, and that is the field of turbulent combustion, because they mix fuel and oxidizer, and that burns on a very short time scale, and we mix hot and cold gas, which cools on a short time scale. And the great thing of this field of turbulent combustion is that they have a lot of funding, and therefore a lot of results we can get inspired from. I don't have time to go into too much details of this, but I just want to mention this one paper from Gerhard Dammköhler in 1940. And it's a remarkable paper because he both carried out experiments and theory. And what I found kind of funny is that, even in the abstract, he kind of said, well, there's so much results in this paper, you have to go and read the conclusion to see all of it. I think that's kind of neat. Now, one thing he realized is that what is important to understanding the burning rate is the turbulent flame speed here, ST, and not the laminar one, which is the one, of one single flame front. he also realized that there are two regimes, and these regimes are given by this dimensionless quantity of the turbulent time to the reaction time in these flame fronts. And later on, this was called the Dampf-Köhler number. And in our case, the reaction time is given by the cooling time. So, and you see, you know, Brian put here this Dampf-Köhler number on the upper x-axis. You see of the mixed gas, and you see that this divides these two regimes actually quite well. Now, armed with this new knowledge from this turbulent combustion field, we can understand this mass growth maybe a bit better. So we characterize it now by this turbulent front velocity, which we can write using diffusion coefficient divided by some characteristic reaction time. Now, in the well-stirred regime, everything is well mixed, and therefore the gas can cool freely. So the reaction time is just the cooling time of the gas, which gives us this 1/2 scaling observed in simulation. But in the corrugated flame regime, it's a bit more complicated. There you can see from the morphology that the gas cannot propagate freely, but the strong cooling leads to a certain characteristic length scale, which we call this turbulent field length, which is the scale where cooling and turbulent diffusion balance. And, you know, if you plug all this in, you actually get this -1/4 scaling also observed in simulations. But the neat thing now is that if you remember the definition of the Dampf-Köhler number, that's, you know, right here. And there has been actually work in this combustion literature that found this 1/4 scaling even with experimental data. So basically infinite resolution, which gave us some hope. Now, that was maybe a bit technical, but, you know, to come back to these initial questions, why do we find this convergence in total mass growth? Why is the total mass growth rate given mainly by the cold gas sound speed and not the hot gas? And what about these weird scalings? I talked a lot about the scalings. And in terms of convergence, well, you know, Drummond already said a lot about this, so I mean, I don't have to say, I guess, anything. It's basically, you know, your numerical diffusion, which is, you know, your laminar diffusion in the case where you don't have thermal conduction, is much smaller than your turbulent diffusion. So one way to think about this is like, you know, mix cream into your coffee. What you would have to resolve is the motion of the spoon and not the molecular diffusion between cream and coffee. The other question was, you know, about this. Why is the speed mainly CS cold? Now, for a shearing layer, you know, you can say your turbulent speed is L divided by your Kelvin-Helmholtz time. So you plug this all in, and so you find that it's CS cold times M hot. So commonly in the CGM and for this experiment, the Mach number is of order unity. For our pulsations, what I showed you, you know, the cold front, excuse me. So basically all the mass is moving at the cold gas sound speed, and therefore also the mixing takes place roughly at this velocity. Okay, excuse me. So now there's actually a lot of cool things you can do with Brandt's results. So, well, these scalings that I just explained you where they come from, you know, you wrote them down, and this is important. For example, if you want to develop a subgrid model of cold gas, there's a lot of talk about this in the literature. And so he, you know, characterized this scaling from U prime to Q, which is our universal scalings backed up by this field of turbulent combustion. And then for this certain geometry, so this shearing layer, what U prime is. And secondly, you know, contrary to what has been previously thought, it's not necessary to resolve the field length. And the side effect of this is that, you know, thermal conduction is pretty unimportant for the total cooling rate. So he varied this here over some values, and you see overall the total cooling rate is pretty constant. Now, on top of that, he also constructed a mixing length model. And so he calibrated this turbulent diffusion coefficient from adiabatic simulations, and that allowed him to, you know, reproduce quite well, actually, I mean, very surprisingly well for me, the simulations with this simple model. So here is an example of this. That's the temperature profile of one of these mixing layers, you know, or two with different cooling strength. And as you can see, the model reproduces these simulations quite well. And that's maybe interesting for people who want to, you know, compare it to 06 emission or something like this. Okay, but let's get to our pulsations and this continuous mass growth. So the question I would like to ask now is, what are really the requirements of these pulsations? So there's one obvious one, of course, that you need a large enough cloud so it's out of sonic contact. That's already been, conjectured by Mike McCord and others. And so indeed, here I perturb this cloud, so I get these pulsations. But on the left-hand side, the cloud is small, so it's in sonic contact, and the right-hand side it's large. And if you look at the pressure slices in the bottom, you see that there are these pressure differences develop on the right-hand side, but not the left-hand side, just as expected. And this large enough cloud, I ran simulations over several over densities, orders of magnitude in cloud size, different resolutions, and you see over order of magnitude it follows this 1/4 scaling actually quite well. Now the second requirement you need to get these pulsations is that your initial perturbation has to be somewhat large. This is shown here on the plot to the right, where I show again this mass growth rate, and this time as a function of these perturbations. And you see, you need perturbations order unity, but then further enhancing your perturbation does not increase your further mass growth rate, which is quite interesting, I would say. Now, on the other hand,
about 5 minutes.
Oh, damn. Okay, thanks. Now, on the other hand, these perturbations, they cannot be too large. And what I mean by too large is that the final overdensity, it cannot be larger than some critical overdensity, which is of order of 300. What happens then instead is that, your cloud just explodes and breaks apart. And I show this here in this plot where, this red line shows final overdensity of 300. And we find, that in this regime, you have this breaking up, and in this regime, you have these pulsations. Now, where this boundary came from, you can look in detail here. I've again 2 simulations just adjacent of this boundary, and you see both of them break up, but then the left-hand one, it kind of gathers quicker than the other. You see this nicer here. I plot the number of small droplets as a function of time for these 2 simulations shown in red and blue. And if you look at, we have similar amount of droplets for both of these simulations initially, but really in this simulation, these droplets seem to, coagulate. And that's what we argue, is that this critical boundary between these pulsations and this fragmentation is a competition between, your initial drop, so to speak, how much do you perturb it, and coagulation. So what really drives this coagulation? So now let's make an even simpler experiment. I have one bigger cloud here in the center and some small droplets around. I perturb it, and what happens is that the inner cloud grows, the outer droplets move towards this, and that's of course because you have this mass growth of the inner cloud, which brings in hot gas, and this hot gas entrains these droplets. And as I said, I don't have time to get in details, but as I said, you should think about this TCL over T floor is your height of the drop, and then your chi initial is proportional to your relative cooling strength. That's where this depend on the final overdensity comes from, and it's not just dependent on the height of the drop, which I found surprising in the beginning. You can go on and model this coagulation in more detail. You can ask, and that has been addressed before by Pratik, what is the important entrainment process here? Is it the pressure, or is it the mass transfer? And if you plug in numbers, you find for these droplets, it's clearly the mass transfer. We also argued this is the case for these bigger clouds, but we can discuss that maybe later on. Now, with this really simple model of coagulation, you can go on and make a bunch of experiments. You can place your droplet at various distances and perturb it, have different overdensities. So here in the solid lines, I show you the simulations, and the dashed lines this very simple theory, and you see overall it seems to reproduce this coagulation quite well. In 3D, it also works. Before were simulations in 2D, it works. But of course, as many of you probably thought, well, it's much slower because you have an additional degree of freedom where your hot gas can move in. But still, if you have many droplets and they all grow, what happens is that they will all coagulate. And again here, solid lines is the simulation, dash the theory seems to work quite well. If you have less droplets, this coagulation process happens less fast, more slowly. Now, one thing that you might ask yourself is, well, here the droplets, they were rather big, so you had these pulsations. What happens if you don't have them? And happens what you might expect. Everything looks quite different, and this coagulation process happens on a much larger time scale because there's less cooling and therefore much slower coagulation. Okay, so to come back to this initial question, what clouds go to the party and which ones will die? Can coagulation save those that are too small to go to the party? I mean, to answer that, there's really one big elephant in the room, and I hear Evan Schneider is shouting that over Zoom right now, and that is turbulence, like larger scale turbulence. And she showed us in this great paper this year that there is a lot of turbulence going on, clearly in the CGM, in the winds themselves. There's not just the radial motion. So this is important to really answer this question, and maybe she talks about this a little bit tomorrow. I just want to say that, can coagulation save the doomed here? So the same setup as before, but this time I stir it with a Mach number of unity. And you see, the cold gas mass is dying, that the coagulation is not strong enough to make them survive. And that makes sense, right? Because if you think about this, coagulation speed was smaller even than your cold gas sound speed, whereas this turbulent velocity is of order of the hot gas sound speed here. So there's not much hope here. Unfortunately, maybe in some quiescent regions where this turbulent velocity is smaller than this coagulation sound speed, there it seems to do coagulate and you can make these clouds alive. Okay, back to this first slide, but this time not the wind tunnel simulation, but these turbulent simulations. So here I have droplets as before, smaller than this critical cloud radius given by a T-cool mix over T cloud crush. And here one where it's larger than T-cool mix over T cloud crush. And you see that this cloud in this turbulent medium is not only surviving, but again we have this mass growth we all talked about today. And I think I'm out of time. So yeah, let me just leave these conclusions here.
Great, thanks, Max. And I really enjoyed also the very Day of the Dead appropriate talk title. So thanks for that. So are there any questions? I do see raised hands. Okay, so let's go to Kartik Sarkar. Go ahead.
Hi, Max. Excellent talk. Just wanted to ask you the snipe question. So what is the length scale, physical length scale of this cloudlets that you are considering?
Yeah, good. I mean, good question. So I normalize everything here to either this critical cloud radius, which I define by T-cool mix over T cloud crush to be unity. So that's the one Pratik was mentioning. We wrote in our 2018 paper about. So that's of order of 2 parsec or so for certain parameters, and then. I sometimes also called L shatter. I define that to be the minimum of CST cool. So that's of order of 0.1 parsec or so in a medium of, yeah.
So in the simulations where you take the effect of turbulence in this cold cloudlets. So I would assume that this broader or the diffuse medium is hotter. And I mean the thing is that. Whether the assumption of the fluid itself is valid at those scales when you consider interaction between a more low density medium and such small cloudlets, like because the mean free path of this diffuse medium and the hot and diffuse medium may be much higher than the size of the cloudlets, isn't it?
No, I think you're still safe with ideal MHD if you're referring to this.
Yeah, it's just referring to the mean free path of the background medium compared to the cloudlets.
Yeah, there's a long discussion on, if like, so for the CST cool length scale, there's a long discussion about this in Mike McCord's paper. And in our, so in most of the stuff I'm talking about is roughly an order of magnitude larger than that. So I think it's still smaller than the mean free path. Larger, sorry, yeah.
All right. We also have a question from Alankar. Go ahead.
Hi, Max. Sir, am I audible?
Yes.
Yeah. Hi, Max. It's a really great talk. So I might have misinterpreted a part of the place where you were talking about this analytical 1D results, and you are trying to compare that with cooling, turbulent cooling layers with very high radiative cooling. So the thing is that when you are comparing with the 1D analytic results, because the thing is 1D, you don't have turbulent, right? So then how are you making the comparison ultimately with this turbulent mixing layers?
Right. Sorry, I don't see you, so I can't look at it. Okay, but so basically you're referring to to Brand's
Right.
yes. So I mean, basically, the question here, or why I showed this, is that here, I mean, 1D is great because you have an analytic solution, which is this red line, and then you can write down, what you have a field length, you have conduction, and then you get exactly the behavior you would expect, right? It just visualizes this puzzle here even more, right? Because a lot of people would say, if you don't have thermal conduction in here, you cannot resolve the field length, and you need to resolve the field length in order to get this converged mass growth also in 3D. But as we showed, and Drummond said, what is important really is that you resolve this turbulence, and therefore your turbulent diffusion is greater than than the one given by thermal conduction, and so it's pretty unnecessary to resolve the field length. Does that answer your question? Maybe.
Yeah. So these data points are from some 3D simulations which you are
this
comparing.
Is all 1D.
Okay, I get it.
There is, in Brand's paper, there is one where he actually put in the 3D curves, and he compares this to the 1D. So I recommend you checking out Brand's paper in general, not just because of this, but there's a plot like that answers your question.
Okay, thanks.
Sure.
Great. Yeah, we have time for another question or two. So Su-Xing, I see your hand is raised.
Yes, so thank you very much, Max. So I'm very surprised to see your latest updates that is very important results, because previously when I also played this problem a little bit, I found that if something is cooled down, so the local density, the local temperature of the cool gas is low, then the local Mach number is larger than 1. So you develop a shock across the cool clouds, and the shock can quickly downhiss into cold clouds and dissipate the cool clouds. So can you talk a little bit more? So whether this really happens in the simulation, and what is the main reason the cool clouds can survive even if you have the stir turbulence?
Right. Thanks. Yeah. So I mean, I'm not saying all the clouds will survive, right? They only will survive if they're larger than this critical cloud radius given by T-cool mix over T cloud crash, and yeah, basically, this T cloud crash should be evaluated using this turbulent, so the average or maybe the average speed of your hot medium, right? So not like the one in the quiescent region, because you might say, there's some droplets that are entrained here, but you're right, they will be destroyed because they are not larger than this critical cloud radius. So I mean, that's all I can say. I don't know if your simulations have fulfilled this criterion, but that's at least the criterion I find to make clouds survive even in a turbulent medium. It would be nice to chat, actually. Yeah.
Yeah, of course. Yeah, inshallah.
Great. Well, thanks everyone.